Drop a splash of milk into your tea, and the swirling patterns it makes will never spontaneously unmix. Yet on a microscopic level, the fundamental equations of physics do not care which way time flows. If you are to watch two isolated molecules bounce off each other, you couldn't tell if the film was running forwards or backwards. We know that energy is never created or destroyed. The universe contains the exact same amount of energy today as it did at the beginning. If the total energy remains constant, it raises a simple question: why do things break down, cool off, and eventually die? There must be an underlying mechanic governing reality that overrides the mathematical symmetry of fundamental physics, forcing the universe to move strictly in one direction. In the 19th century, a physicist named Sadi Carnot was attempting to design a better steam engine. He realized that even if an engine had zero friction and perfect insulation, it could never be 100% efficient. Every time the engine completes a cycle to push a piston, a portion of the heat must be permanently dumped into the colder surrounding environment to reset the mechanism. That specific energy becomes locked away, unable to do further mechanical work. German physicist Rudolf Clausius studied Carnot's limits and recognized a broader pattern in how energy behaves, coining a new quantity to measure it: entropy. Entropy is commonly described as disorder, but it is more accurate to view it as the unstoppable tendency of energy to spread out. This continuous diffusion of energy is the physical reason why a hot cup of coffee gets cold, and it is the sole reason why time has an arrow. To understand why energy inevitably spreads out, we have to look at the work of Ludwig Boltzmann. He realized that thermal energy is simply discrete, tiny packets of energy continuously hopping back and forth between atoms in a structure. If you start with a highly concentrated cluster of energy packets in one corner, those packets will continuously hop randomly between the available atoms. Statistically, there are millions of ways for those packets to be mixed evenly across the entire grid, but only a handful of ways to remain perfectly clumped in that corner. Heat flowing backward from cold to hot isn't completely impossible, but with everyday objects containing trillions of atoms, it's so mathematically improbable that it never occurs. The universe is not governed by an active force seeking to destroy structure. It is simply moving blindly from highly unlikely concentrated states into highly probable, evenly diffused states. If the entropy of the universe is constantly increasing toward a spread-out state today, then yesterday it was slightly more concentrated. Trace this timeline backward, and you find that the universe must have started in an ultimate state of absolute, tightly bundled concentration. This heat map shows the cosmic microwave background radiation. It reveals that right after the Big Bang, the early universe was extremely hot, dense, and almost perfectly uniform in its temperature across all of space. You might expect a smooth, uniform soup to be a high-entropy state, but once you introduce gravity, matter naturally wants to clump together into dense pockets. In a universe governed by gravity, a perfectly smooth distribution is actually an extremely unlikely low-entropy starting point. As space expanded, matter fell into those gravitational wells. That motion converted enormous amounts of potential energy into kinetic energy and heat, igniting the slow, steady unwinding of the cosmos, creating all the structure we see around us, from the massive galaxies to the burning stars and the orbiting planets, requires burning through vast amounts of useful energy. The resulting dispersed waste heat from all that celestial construction needs a final destination. Theoretical physicist Stephen Hawking proved that black holes are not completely dark. He calculated that they actually emit a faint radiation, possess a measurable temperature, and hold colossal amounts of entropy on their surfaces. When physicists calculate the total entropy of the modern universe, they find that the stars and gas clouds contribute almost nothing. Nearly all the entropy that exists today is tied up inside black holes. Every event in human history, every thought you have, and every action you take is occurring within this massive statistical unwinding, as matter and energy slowly fall toward these ultimate cosmic sinks. Returning to Earth, there is a systemic paradox in our own atmosphere. For most of its history, the Earth has radiated the exact same quantity of energy back out into deep space as it receives from the Sun every single day. If the energy going out matches the energy coming in, the difference lies entirely in its quality. The Sun delivers a steady stream of highly bundled, low-entropy energy directly to our surface. This has led biophysicist Günther Wicken to propose that life is not a rebellion against the laws of thermodynamics. Instead, biology exists as a highly efficient mechanism to accelerate the spreading out of energy. Plants capture that concentrated sunlight to grow, and animals consume those plants to move and survive. For every single high-energy photon a leaf absorbs, the biological system ends up expelling 20 dispersed, useless photons of waste heat back into the environment. Life thrives here specifically because living organisms are spectacularly good at taking the Sun's low-entropy fuel and converting it into the high-entropy waste the universe statistically demands. Trillions of years from now, the final stars will fade, and every supermassive black hole will eventually evaporate. This is the heat death of the universe. All available energy will become so completely and evenly spread out that no mechanical work can be done, and nothing interesting will ever be able to happen again. In this final state of absolute diffusion, the arrow of time itself will disappear. Without any concentrated pockets of energy left to transition away from, there will be no physical way to distinguish the future from the past. Both extremes are featureless voids. True structure exists only in the fleeting transition as the universe winds itself down.